Determinants can be difficult to compute, especially for large matrices, but we can use some of the properties of a determinant to actually greatly simplify the calculations in many cases. So I'm going to list some properties. These you'll find these in the textbook. First property is if A has a row or column of zeros, then the determinant of the matrix is 0. So again, that would be easy to prove using the cofactor expansion. If an entire row is all zeros, then the determinant is 0. Okay, and then let's look at what some of the elementary matrix elementary operations, what effect they have on the determinant. Swapping two rows or columns in a gives a matrix with determinant equal to the negative determinant of the original matrix. So anytime you swap two rows or two columns, the determinant of the new matrix will be the negative of the determinant of the original matrix. If a row is multiplied by k, constant k, then the determinant of the new matrix is k times the determinant of the original matrix. If two rows or columns are equal, then the determinant of the matrix is 0. And then the last one goes back to another elementary row operation. If a multiple of one row is added to another, the determinant is unchanged. And this last property is one that you can apply to greatly simplify determinant calculations. So let's look at an example. This is exercise 3.1.5 C, where we're asked to calculate the determinant of a 4x4 matrix. Again, in general, that would be pretty difficult or time consuming. -1, 1, 1, 0 in the first row, 2, 1, 1, 3, 0, 1, 1, 2, 1, 3, -1, 2. Okay, and then I'm going to use property number 5 here to actually try to get some more zeros in the first column here. And property 5 doesn't change the determinant, so -1, -1, 1, 0. For row 2, I'm going to replace it with row 2 plus 2 times row 1. So adding a multiple of another row to this row, of course that gives me a 0 here, -2 plus 1, would be -1, and then 3, and then 3, and then 0, 1, 1, 2. And here I can simplify, get rid of the 1 here just by adding the first row to the fourth row. Again, this doesn't change the determinant. So 0, 2, 0, 2. Okay. I can actually pretty easily calculate the determinant here, but I'll take it one more step. I could expand along the first column because I've got only a single non-zero element, and then we just have to take the determinant of this corresponding 3 by 3. But let me take one more step to introduce some additional zeros below this leading 1. 1, 0. It's the first row. 0, -1, 3, 3. And then add row 2 to row 3. So I'll get 0, 0, 4, 5, and then add 2 times row 2 to row 4. So I get 0, 0, 6, and 8. Okay, and then now even for this 3 by 3, expanding along this first row, here's the only non-zero element. I need to determine find the determinant of this corresponding 3 by 3, but in this 3 by 3 matrix, I've got only a non-zero element along that first row. So this is equal to, this would be in a plus position, so -1. Okay. Now times the determinant of this 3 by 3. Now this is still in a plus position, so it'd be -1, expanding along this first column. But here now I've just got this 2 by 2 left, so it'd be 32. 4 times 8 is 32, -6 times 5 is 30. So that's -1 times -1, or +1 times 2. And so I pretty quickly, using my elementary row operations, in particular this property of adding a multiple of 1 to another. Now, the other operations, I have to be a little careful. Anytime if I swap 2 rows, I need to include a minus sign out here. And if I multiply a row by 3, then I need to divide by 3 out in front to maintain the equivalence based on these properties. Let me give you 2 other properties here that are useful, and I'll do 2 more examples, 2 other properties. One is the determinant of, now this is multiplying an entire matrix by k, a constant k. Equivalently, I'm multiplying all rows by k. So that's kn times the determinant of A. And then another one is, so if A is triangular, that means, a triangular matrix, it can be either upper triangular, where it has elements, may have elements along the main diagonal and above that, but no elements, or all the elements are below the main diagonal or 0. Or it can be a lower triangular matrix where all the elements above the main diagonal are 0, and I've got elements, non-zero elements just along the main diagonal and below that. In either case, if A is triangular, the determinant of A is really simple. It's just the product of the n elements along the diagonal, AII. From this immediately we get the determinant of any identity matrix is going to be 1. So I could actually use this. Let me go back to this previous example, and where I think the last determinant I had was minus 1, 0, 0, 0, minus 1, minus 1, 0, 0, 1, 3, 4, 6, 0, 3, 5, and 8. Now I'm going to use some additional row operations to reduce this to upper triangular form, and not all the way to row echelon form or reduced row echelon form. In order to eliminate the 6 here, what I'm going to do is multiply the third row by 6 and the fourth row by 4, so I have identical elements here. But if I do that, I need to divide by 1/6 and 1/4 to maintain the equivalence. So minus 1, minus 1, 1, 0, 0, minus 1, 3, 3, 0, 0. And again, I'm multiplying this row by 6, so I have 24 and 30. And multiplying this bottom row by 4, so I have 24 and 32. I'll write down my operations. I replace this row by 6 times and this row by 4 times. Again, so I have to divide by 1/6 and 1/4. Okay, so I'm going to combine that as 1 over 24th, 1 over 24 rather, minus 1, minus 1, 1, 0, 0. I wrote down a minus 3 there, but that was an error. That should have been a minus 1. 3, 3, and then I'll keep this row 24 and 30, and then now I'll subtract from row 4 row 3. This doesn't change the determinant, but it gives me a 0 here. And then now I can quite easily, this matrix is in upper triangular form. There are no elements below the main diagonal, so makes it really easy to compute the determinant. It's just the product of the terms along the main diagonal. So I'll have minus 1 times minus 1 times 24 times 2. This is plus 148 divided by 24, or 2, which is exactly the same answer I got previously. So, a couple extra steps to reduce the matrix to triangular form, and then easily find the determinant. Don't have to do even any sort of cofactor expansion or anything like that. The only tricky thing here is, again, if I multiply a row by a constant in order to maintain that equivalence with the determinant, I have to divide by the constant out front. And then also, if we invoke any row swap operations, I'd have to multiply by minus 1 out front. Let me do one final example. Some of the examples at the end of the section actually are kind of algebraic, so they're not entirely numeric. But let's look at 3.116D, where we're asked to find values of x and y such that the determinant of this matrix is 0. So it's xy 0, 0, 0, xy 0, 0, 0, x, y, y, 0, 0, x. I guess encouraging you just not to be overwhelmed by these problems. They're actually pretty simple. You can take the same approach of finding the determinant. We can expand along any row or column. I'm just going to expand along the first column here. So I've got this element x, which is in the plus position, x, and then I'm going to find the corresponding determinant of this 3 by 3 matrix. Well, I see that this 3 by 3 matrix is upper triangular, so the determinant of this 3 by 3 matrix is just x cubed, the product of these 3 terms along the diagonal. So I have plus minus, so I'm going to subtract this cofactor term corresponding to y. So y, and then eliminating this row and this column. And looking at what's left, I see I have a lower triangular matrix. All of the elements above this diagonal of the resulting 3 by 3 are 0. So again, quite easily, the determinant here is y cubed. We're asked to find values of x and y so that the determinant is equal to 0. So I set that equal to 0, and I get x cubed is equal to y cubed, or the determinant is going to be 0 as long as if x is equal to y. So for any numbers, x and y, as long as it doesn't matter if they're both 10 here, or both 3, or both pi, or both 1,000. If the matrix has this form, it'll have a determinant of 0. The last thing I'll mention is, in all your work, at least for the numeric problems in Octave, you can just use the function det to verify your determinant calculations. That's it for today. Actually, I think there's a couple more sections in Chapter 3. We're going to finish linear algebra. When I finish up Chapter 3, I'm going to switch over to numerical methods. So a couple more lectures. Let's see, it's Wednesday today. No class on Friday because of the Easter holiday, so I won't post any more lectures after today until Monday. So enjoy your break, and I will see you next week.